The second part of the video lecture series on especially shear wall design using ETABS program. In the previous video, we have discussed about the requirements and the design principles that are required to successfully and comply with the code requirements, successfully design the wall and comply with the code requirements. In this video, we will give you an introduction to the model and the fire assignment to the shear wall. So this is a residential building and we have a lift code here. For this, we are proposing a shear wall. And all of the members are the columns. So this may be either special moment frame columns or intermediate moment frame columns, depending on the chosen lateral load resisting system. So here, these are the beams along the wrong direction. The yellow ones, the cyan colored ones are the actual beams, which have a 12 and 12 by 20 inches depth. These are actually not beam. These are connector elements, which are modeled in the model or kept in the model. However, they do not have any work in the model, or we are not going to design these connector elements from the model. Model will be used to design the connector elements, but we are not going to design them as beams here in the model, okay, or columns in the model. We have assigned or drawn these connector elements in the model to make it understandable, to convey a message to our young engineers that you have to provide here collector elements when you detail your structure. So, for example, you see that this shear wall leg, this one is directly connected to the slab, and there is no beam connected to the shear wall. So you have to provide a collector here, right? Because you will collect the shear from this portion of the diaphragm and transfer the shear to this leg of the wall. So how are you going to transfer this? You have to provide a certain amount of longitudinal reinforcement which will be developed into the wall. That will behave as a collector here. Again, here, if you look, this is a large amount of diaphragm here, almost 90% maybe. So this area's shear, or the mass, or whatever you say, the shear that will be produced by the mass located in this diaphragm will flow towards these two legs, one here and the other one here. Almost all of it. Columns will bear very less of the shears actually. So here we have a beam which we can provide some additional reinforcement in it to account for the collector reinforcement behavior. However, you see that we do not have any structural beam along this line. This is a collector. This color, what is this? Maybe violet color. So here we do not have any beam along this line. So we have modeled this or kept in our model to remind our engineers that you need to provide a collector here. So its stiffness can be reduced in model so that it doesn't interfere in any design procedure here. But also it is okay not to model it at all, because modeling it is not necessary. So we just model it to convey to our engineers that we are providing here some collector elements. To talk about the model, since we have placed the structure shear wall not at the center of the diaphragm, say if we had provided the structural shear wall here, then probably there would be no torsional irregularity in the structure. But you see that the wall is offset from the center point, along both the axes. With respect to both the axes, the wall is offset. So we are bound to have torsional irregularity with respect to both the axes. We have torsional irregularity along this axis because this part is very stiff with respect to this part. This part swings with respect to this. Again, when we apply lateral load towards this direction, then this part is very flexible or soft with respect to this part. So this part will swing with respect to this. So there will be torsional irregularity again. We have chosen a wall thickness of 12 inches, and below the ground we are using 4 inches wall thickness. These are 4 inches wall, and this is a 12 inches wall thickness. We will basically design this wall and demonstrate the wall design of this part, because this has a maximum bending moment in the model. Now let us talk a little about the pier assembly procedure. Okay, so this is a compound wall. Compound wall means that it has a lot of segments in it, and all of these segments are connected to each other by its perpendicular walls. So you do not assign individual piers to these walls. Okay. So for example, how many segments are here? Here are 5 shells. You do not assign 5 piers because this one is a single member. This is resisting the bending moment as a whole, shear as a whole. However, there is a distribution of shear force from leg to leg based on their stiffness and arrangement. However, the total of it is resisted by the whole member. So it is logical to assign a single pier to these walls. So you can assign a single pier, shell, pile level, and P1. I have already assigned pile level to my walls. You can see that these are P1. All of these are P1. If you assign separate pier element, then there will be some misconception. For example, if say, let me clarify it to you. Let us look at the bending moment first. Does it look like actual bending moment or not? Look at this here. The bending moment is at the top. It is 0. Then some portion of it is positive, and then it's become negative, becoming 7,000 cubic feet at the bottom. And moment 33 will be less, about 700. And for QY, there will be moment 33, very high amount of moment 33, 7,300 cubic feet of bending moment. Okay. So let's say now that let's work with this portion only. This one, we are assigning it another pile level. Say it is pile 2. Okay. And then it is say pile what? Pile 3. Okay. Say it is pile 4. And this one you can assign here pile 2 as well, because it is pile 2. It is pile 2. Let me okay. Okay, let us look at the bending moment now. You have a lot of bending moment now. It is 5,000 cubic feet here. It was supposed to be 7,000 cubic feet here, but you see that you cannot now develop the total bending moment by summing this all. For example, here it is 2,400. Here it is 1,400. So it is 3,800. Now you need the bending moment of the one of this wall and this wall. The bending moment of this walls will be M2 for the same load. These are 8 or 16 and 10. 16, 10 is actually, say they are 0. Then how much is it? 3,800. But how much bending moment did you have in your wall actually? The wall, this wall is resisting all the bending moment and controlling the drift and displacement of your building. So this wall must be resisting a lot of bending moment, right? So how much is it? How can you understand how much bending moment your wall is resisting? You cannot really capture it unless you assign a single pier to your walls, all your walls. So you must assign P1. And then again, if you look at the bending moment now, then okay, it's good now. You get the minimum actual bending. But don't be mistaken that, say, for example, if you had more walls, say these are also your walls. Say you have a few more walls. Say this one is also a wall. Say this one is also a wall. So these are separate, not connected to each other by as like this one, right? This is a compound wall, but these are separated wall. They are not wall in my model, but let us consider them wall. Okay, if they were walls, then what would be our assumption or consideration? We would assign different pier section to them. For example, it has P1. Say I have more 4 walls. These are all the walls. So since it has P1, we will assign here P2 to it, P3, P4, and P5. Okay, you cannot use a single pier to more than one member in a story. Say you have assigned P2 here, you cannot assign P2 again in your floor in this story. You cannot use P2 for it or it or it, but you can use P2 for your same member vertically. There is no problem using the same pier level vertically. For example, this wall has P1 vertically, whole height. Since this is a single member, we have P1. But since these are different members, they will have different pier levels, P2, and P2 will be continued vertically up to the whole height. Okay, this one P3, P4, P5. However, there is no order or sequence by which you need to assign your pier level. You can name it anything P1, P2, or you can name the pier level by your name as well. For example, if your name is um, whatever, you can name your fire by that name as well. Okay. Uh, that was a preliminary introduction to the fire assignment and our model. We will uh, discuss in detail about the structural design of our wall from this model in the next two videos. Thank you.